So welcome everybody to the last session of the workshop. And thanks for sticking around. So it's a pleasure to introduce Ben Moseley, who's the Carnegie Boss Assistant Professor of Operations Research in the Tepper School of Business at Carnegie Mellon University. Ben works broadly in operations research, theoretical computer science, and machine learning. And like many of the other talks, this talk today will be putting together those topics in an interesting new light. Ben, take it away. I will be monitoring the chat for questions, and I will inject them at opportune moments.
Sounds good. Well, thanks so much for the introduction, and thank you to all the organizers for having me here. I'm very happy to speak at this workshop. Right, so I'm going to talk today about learnable and instance robust predictions for matchings, flows, and load balancing. And I'm Ben Moseley, and I'm in the Operations Research Group at the Tepper School of Business. And I also do a day a week at the startup Relational AI. Okay. So before I start this talk, first, I would just like to thank my collaborators. So really the brains behind this work are two students, Thomas Lavastida and Chen-Yang Xu. So Thomas is my student at CMU in the OR group, and Chen-Yang is at Zhejiang University in China, and he came and visited CMU for a very difficult year during COVID. But luckily, we got this amazing work done together. And also, this is joint with R. Ravi, who is also in the OR group in the Tepper School of Business. So the results from today come from two different papers. So one paper has the same title as this talk, which is to appear in ESA this year. And the other paper is using predicted weights for ad delivery, which is going to appear in the conference ACDA. So we've been hearing about how we can use machine learning to improve algorithm design. Now, what I would like to do is just take a moment and spend just a couple minutes giving my own pitch for the area. And then this will feed into how I'm going to think about designing models for this setting. So we all know that recently machine learning has been very hot and has really been changing society. So there's been a lot of technological breakthroughs recently driven by ML. So self-driving cars, computer vision, speech translation, etc. Now, while machine learning has been touching a lot of aspects of our lives, one question is, could machine learning change the way we think about designing combinatorial optimization problems? And so this is the kind of question that I am very interested in. So one of the main problems that we try to solve in practice is, well, okay, so there's a question is, what algorithm should I use to solve my problem? And now, usually what you're going to do is you're going to go try to find some kind of analysis to help derive which algorithm you're going to use. And so that is, to pick an algorithm for your given application, you need to have some sort of modeling framework to show that there is a good algorithm to pick. Now, ideally, what we want to have is an algorithm that performs well for the kinds of input instances that we actually see in practice. So in the ideal world, we wish we could have an algorithm that is exactly tailored to the kinds of input instances that we're actually seeing in our given application. Now, unfortunately, though, it's usually very hard to well characterize the kinds of input instances that we're actually seeing in practice. So it's usually hard to write down a formal mathematical model for exactly the instances that we're going to see. So usually, what do? Well, we revert back to some stylized form of analysis. So maybe we go to the worst case analysis setting, or perhaps we go to the stochastic analysis setting. But in both of these settings, we typically lose something. So for instance, if we go to the worst case, then when we're trying to find a good algorithm using worst case analysis, often we spend a lot of time trying to design algorithms for pathological input instances that we never actually see in practice. Now, similarly, if we go to stochastic analysis, often it can be hard to define the exact kinds of distribution that we're seeing in practice. And moreover, practice often has complicated correlations that are, they're just hard to model, or it's going to be difficult to actually prove anything about an algorithm for these types of distributions. Now, while this is true, what we wish we have is an algorithm that's close to the instances that we actually see. So the idea of this recent work is that, well, what we might do though is look at data for the problems that we have. So that is, for lots of our applications, we have access to lots of data from the past. And
Ben,
yes.
Ben, may I interrupt you? Are you moving your slides?
No, I'm just having one little short rant here for just a moment.
Great. Okay.
Thank you,
Making sure nothing broke. Okay, good.
Yes, yes. I just want to spend a minute here. So, good. Now, instead of using these more classic forms of analysis, what this emerging line of work is doing is looking at, can we learn something from the data on our applications and then take that learned information and give it to the algorithm. So for example, say that I'm scheduling jobs in a data center. Well, I've seen jobs yesterday, the day before that, etc. So maybe what I'll do is I'll learn something about these instances, take that learned information, give it to the algorithm, and then the algorithm can self-optimize to the kinds of input instances that we actually see. And so in this way, we have an algorithm that is becoming close to instance optimal. And so this is the area that we'll be talking about today. Now, recently, there's just been an explosion of recent work on this topic. So I just can't get away from results in this area. So I've been active at NeurIPS, ICML, ICLR. I keep seeing papers on this area. So how do we create good predictions that combinatorial optimization algorithms can use to solve problems? Similarly, I've seen this in other communities like SODA, ESA, etc. So there's clearly a lot of interest in these kinds of problems. And I can't summarize all of the recent work that has been going on in this area. But what I want to do now is pose to the community some challenging questions that I think future work should try to look at. Now, the one thing we can take away from this previous work is that indeed ML can be combined with classical combinatorial optimization to achieve better results. So what's emerging is that we can discover better algorithms, and there are interesting algorithmic questions here that we can ask about, what kinds of predictions can we give to an algorithm, and which kinds of problems can we obtain significantly better results than other forms of analysis using these kinds of predictions. Now, the thing that I personally think that is extremely exciting about this research area is that it gives us a systematic model for going beyond worst case analysis. And so what do I mean by that? Well, for many years now, we've been interested in designing generally applicable beyond worst case analysis frameworks. However, it's been really hard because often our beyond worst case analysis frameworks have to be extremely problem specific, and it's hard to design one model that we can apply in lots of different places. However, here, using this prediction setting, models are emerging that we can apply, say, to any online problem. Or as Sergey was talking about, a model there is emerging that we could say apply to any offline problem for improving the worst case running time. And so this, I think, is particularly exciting about this research area. So what is the model that I'm talking about? So here I want to talk about the model as at a very abstract level, and then we'll get into the details. So the way I think about this, right, is so we have data that we can learn from. So what is that data? So to me, that data is prior input instances of the problem being considered. So if we're scheduling jobs, I can look at the jobs that came yesterday. So the input instances that we've seen in the past. Now, what do we want to do? Well, we want to design an algorithm that makes predictions from these prior input instances to tailor itself to being close to so-called instance optimal. Now, when we do this, we want to design algorithms that are robust to errors in these predictions. And so that is, if we're going to try to learn information from these instances, it's not like we should expect the future instances to exactly be predicted from the past, but rather, ML is going to have some errors when we make these predictions. So for instance, maybe there was a distribution shift, or perhaps a lot of our instance looks very similar day to day, but there's some portions that are, very complicated and perhaps adversarial. And we want to ensure that our algorithm can cope with these errors. So for example, we don't want, say, inconsequential changes in the input instance to result in an algorithm that has extremely poor performance. And so we want an algorithm that can adapt and overcome these errors. Now, if we think about a model of this form, the benefit of such a model, in my opinion, as an algorithmist, is that here we've abstracted away the learning. So we're not talking about, say, improving the deep learning algorithm or say specific methods of learning like random forest, et cetera. Instead, we're talking about, what are the predictions that we can learn such that algorithmically we can use them to get better results. So it's a very algorithmic question that we're asking. So if we think about a model, the way I think about the model, it's similar to what Sergey and Ola presented. And so I think the pillars for a model in this setting should have the following aspects. So first of all, for any result, positive result, I should say, we need existence. So our predictions should allow our algorithm to go beyond worst case bounds. Right? And so this worst case bound that we go beyond, this could be offline in terms of running time, this could be online in terms of the competitive ratio, whatever it is, our predictions should allow the algorithm to go beyond the worst case. So we should be able to break through some barrier using classical forms of analysis. And so the goal here is just discover a prediction that allows you to do this. Now, after we have established that there is such a prediction, then we need some kind of robustness guarantee. Now, I'm not going to pin down exactly what that robustness guarantee is going to be yet, but we need some kind of robustness. So at an intuitive level, whatever prediction we're given, we should be robust to, say, inconsequential changes in the problem input. And so that is, if the problem just changes a little bit, the structure of the optimal solution is roughly the same, right? Our algorithm should not blow up and have extremely poor performance. So somehow we should have a robustness to incorrect predictions. And then finally, this entire area is motivated by the fact that for our applications, we have data that's available. And so here, from that data, we hope to learn something to give to the algorithm. So whatever that is, it should be learnable. So whatever this prediction is that we're going to nail down and show that the algorithm can go beyond the worst case with it, it should be something that we actually can construct from previous data. And so I think to have a result where we have a prediction that we believe it's going to work, we know how to actually construct it, and it's learnable, and then finally it's robust to changes in the input. So some challenges I think that remain for the community are the following. So if these are going to be the pillars to a model, and not, maybe there could be other aspects, of course, but if we're going to think about models that have these properties, there's a question of, well, how should I measure robustness? So for example, and I'm going to talk more about this in just a second, but should I measure robustness in terms of, say, how wrong my prediction is? Right? And so in Sergey's talk, he talked about how far off the dual variable was that was predicted versus the one we should compute. Right? So we measure things in that way. Should I measure things in terms of changes in the problem input? Or there's a paper by Sung-Jin Im et al. That's going to appear soon in SPA. And here they look at, they're going to measure error in terms of how much the optimal solution changes. And so I think a question for the community to ask is, well, what are good versions of robustness? And I can imagine here that there could be many different definitions that make sense. And there might be different trade-offs between using different forms of robustness. And I think it's an interesting question to explore what these are and their properties for different problems. Now, once we have these definitions of robustness, well, then we need to figure out, well, how should we give our guarantees in terms of the error in the input instance? So this could be how much the instance shifted or how wrong our parameter is, et cetera. And ideally here, what we want are bounds that allow us to compare different algorithms. So that is, I should be able to have some formal guarantee or framework that allows me to say theoretically that one algorithm should be performing better than another in certain situations. in the same way we do using worst case analysis. And then finally, the other question is how do we constitute what is a learnable prediction? And so that is, what's a prediction that we can formally learn and that we can actually hope to compute given prior instances of our problem? So, right, so the motivation for our model is that our data can be used to construct our predictions. So then what is this right model for learnability? Similarly, if we have unlearnable predictions, could this lead to a stronger class of algorithms? And so what I mean is, maybe there is a class of algorithms that have learnable predictions and they can be used for some problems. But then there may be other problems or better guarantees that you could obtain if you look at predictions that say are unlearnable, and we can't really hope to learn them from past input instances. So I think it's an interesting open question. What is the power of a prediction that is learnable versus unlearnable? And I haven't seen any results like this. And I think that this would be an interesting question to answer. Now I want to talk a little bit about robustness and how we give our guarantees for robustness for our problems. So there's been several different ways robustness has been given in the past. And here I want to look at one particular way, which I'm going to refer to as parameter robustness. So I think parameter robustness is an extremely interesting way to.
Yep.
Yes. Is there a question? This is a very interesting way to give the performance guarantees of an algorithm, and it's going to allow us to get some intuition that our algorithm is indeed robust to errors in the predicted parameter. That said, I think there's also some caveats here. So what is this parameter robustness framework? So let's say for a problem, I predict some parameter y. So think of this as a vector. Right? So I'm going to predict some vector. And so maybe for set cover, this is the vector is telling me which sets that I should pick. Good. And now, if I consider some input instance, so imagine that I'm going to see some new instance online. There is some correct parameter that I should have predicted for this input instance. And now I was given some other parameter, y hat. And now what I'm going to do is I'm going to look at the difference between the prediction that I'm given and the prediction I should have been given, or the correct prediction for this instance. So let eta be the L1 norm error, or the difference between these two predictions. So for parameter robustness, what people have been showing, or several papers have been showing, are results of the form that I'm going to be some function of eta competitive. And so this says that if there's some small change in my predicted parameter, well, then I can prove that I'm going to be competitive, maybe linear or quadratic, in terms of the change in the parameter I was given versus the parameter I should have been given. So I think this is really interesting, especially when you prove very small bounds here. It shows that you should be robust to changes in the input. That said, I think there's some challenges with this kind of guarantee. And one of the challenges is that it's very difficult to compare across different parameters. So for instance, if you give me one result for some prediction, and then I look at another prediction, maybe I'm quadratic competitive in terms of the error of one prediction and linear in the other, it's not clear to me immediately which result is actually better, because if the predictions are wildly different, they could be on very different scales from one another. And so due to this, it can be hard to immediately tell which parameter would actually give you better performance. Further, this parameter robustness, it's disjoint from learnability. So on its own, I think it's a little bit hard to interpret some of these results. And so one question I have is, can we put this parameter robustness framework on some theoretical footing that allows us to, say, compare across different parameters, or different predictions, I should say. So these are the questions that I think are that the community should be thinking about. And now what I would like to do is discuss our recent work, which tries to touch on these questions. So it tries to explore some of these questions that I'm asking here. And so to do this, we're going to be looking at capacitated online matchings as our problem to carry us through the rest of the talk. So this is just a classic problem where we have a collection of advertisers on the right-hand side. Each of them has some capacity. These are offline nodes we know in advance. And now online impressions are going to arrive. When an impression arrives, we learn of all of its edges to the advertisers. And now I can match it to one of the advertisers in its neighborhood if its capacity hasn't been saturated. And the key here is I have to make irrevocable decisions. So this example will carry us through the rest of the talk. And I'm going to assume throughout this talk that the fractional allocations are okay. So that is, I can allocate one of these impressions up to a fractional unit of 1 to my advertisers. Now, all the results I'm going to be talking about generalize to an online flow allocation problem in DAGs. We're going to be talking mostly about matchings because everybody here, I think, can relate easier with matchings, but these results do generalize to flows, so I want to mention it. So what is this allocation problem? So imagine you're given a directed acyclic graph, and now offline, you have all of the graph except for a collection of source nodes. So in this graph, you're going to have a single sink, edges point towards this single sink. And then you have source nodes that are going to arrive online. And so when a source node arrives, it tells you its edges to the other nodes, and you can route up to a unit of flow from this node to the output. And now inside of here, each of these nodes have some capacity. And when we do the routing of the flow, you have to obey the capacity constraints. Moreover, when a node arrives, you lock in the flow path, so you can't modify the flow later. And the goal is to maximize the flow at the end after all the impressions have arrived. Okay, so for these problems, now I want to talk about a kind of robustness that we investigate in our work. So this kind of robustness we're going to refer to as instance robustness. So what instance robustness tries to do is measure the change in the problem input instance. Now, of course, we need to define exactly what that means, how an input instance changes, and this is going to be a bit problem specific. So here for the matching and flow allocation problem, we'll define an input instance as follows. So take the offline nodes and fix them. Good. And now we're going to characterize an input instance by the kinds of nodes that are going to arrive online. So each node that arrives online, we're going to call a specific type. And so the type is going to depend on the neighborhood of this node. Or in other words, it depends on the nodes that it's adjacent to. Good. So like for matching, a type would just be which advertiser is going to be matched to. And now I'm going to define an input instance according to a vector y over the types. So here the vector says how many nodes are going to arrive of a specific type. Now, this has nothing to do with the order they arrive online. This could be still completely adversarial, but this just describes which nodes will eventually arrive in this vector. Now imagine I compute some prediction y from an input instance I. Okay, so say for every input instance I, there exists some prediction y of I. And if I give that prediction to my algorithm, let's say I go and prove that the algorithm is C competitive. And so this establishes the existence part. So it says that there is a prediction that if you gave me the instance and I give this to my algorithm, then online, no matter how these impressions arrive, the algorithm is going to be C competitive. Good. So for every instance, there is a good prediction, is the way to think of this. Now imagine that we don't actually see the input instance I. So I give you some prediction y of I, but I don't really see the instance I online. Rather, some other instance I prime arrives. Good. So now what I'm going to do is I'm going to measure the difference in the input instance. Right? And so here I'm going to say the algorithm works well for one instance. Well, how well is it going to work for nearby instances, where nearby is defined by the L1 norm difference in these two vectors? Good. And now the idea is we show the algorithm is some f of c gamma competitive, where here gamma is the change in the input instance and c is the original competitive ratio you would have gotten if you were given the correct y. And so the goal here is to show that if you were given an instance that's extremely close, then you should be close to like the C competitive, which should be better than the worst case bound. And then as the input instance changes, your competitive ratio should slowly degrade in terms of the error or change in these two input instances. And so this is the kind of result that you would show in this instance robustness framework. And you could also potentially do a little better and instead show something like, imagine alpha was the best worst case bound. An ideal result would be your sum f of c gamma competitive, but after this gets larger than some value alpha, well, then you just revert back to the best worst case algorithm. So ideally here, you perform much better than the worst case with a perfect prediction. You slowly degrade in terms of the change of the problem input instance until eventually, if the instance is completely wrong, well, then you revert back to say the best worst case algorithm. So the one thing I kind of like about this instance robustness is it's comparable across different parameters. So if you gave me a competitive ratio, right, and I use this instance robustness framework, well, then I can immediately look at those two competitive ratios and tell which algorithm is performing better, right? And so it doesn't depend, say, on the scale of the parameters we're given. And intuitively, it captures this notion that our algorithm should have good performance if there are modest changes to the problem instance. Now, it has its own caveats, and one of the big caveats here is that the definition of instance robustness is going to be extremely problem specific, right? So here we're defining it on this type vector for this matching and flow problem, and I imagine that you have to define some other different kind of metric for other problems. Good. So that was our idea for the robustness. Now, I would like to talk a minute about learnability. So here we can talk about a framework that generalizes the framework from data-driven algorithm design. So the idea is whatever prediction that we're using should somehow be learnable. So what we want is a prediction that we can actually construct from prior input instances of our problem. So the framework that we're going to use is the following. So imagine that our instances are coming from some unknown distribution D. And so that you have an unknown distribution sitting out there, and that's our instances are being drawn from this distribution. Good. Now, for this distribution, there is some best prediction. So that is, there's some prediction y star that would give me the best expected performance for the algorithm if I draw an input instance from this distribution. So for learnability, what we hope to show are results like the following, that using a small number of samples, we can compute a prediction y hat that would give us performance the following with high probability. So the algorithm's performance on a random instance drawn from our distribution using y hat in expectation is at least as large, say, as or within a 1 plus minus epsilon factor of the best prediction. So that is, here, what we're showing is that hopefully using a small number of samples, you can learn a parameter that is close to the best possible parameter that you could use for your given algorithm. An important thing I want to point out here is that here I'm comparing my algorithm to itself. And so I'm not comparing to the optimal solution. So what I'm saying is, for this distribution, can I find the best parameter for my algorithm? Is that computable with a small number of samples? Good. So this is similar to pack learning and data-driven algorithm design. So basically, we're just borrowing this definition from all this this beautiful work that has come out of the data-driven algorithm design area. Now, here I compared the algorithm to itself. We could also generalize this further and compare directly to the optimal solution. And this would be closer to, say, a competitive analysis framework. And so here, what you might show instead is that a small number of samples from this hidden distribution will allow you to compute some parameter y hat such that in expectation, your algorithm's performance is within a 1 minus epsilon factor of the expected value of the optimal solution. So, so rather than comparing the best parameter for our given algorithm, instead we show indeed we could find a prediction using a small number of samples such that we get a good approximation and expectation. And I think both of these could be reasonable models to consider to ground predictions in learnability. Good. All right, so now I want to come back to the problem at hand. So let's talk about what we could predict for matchings and flows. So here we're going to predict weights on the offline nodes of the graph. So that is, each of our advertisers in the matching problem is going to have a weight that we're going to predict. If we have a general DAG, we're going to have weights for every node in the DAG. So the thing that's nice about weights is it's a nice single number, so a simple compact prediction. At some intuitive level, I think of the weights like a lower weight means an advertiser is more restrictive, like you should save its capacity for later arrivals, and a higher weight means the advertiser is less restrictive. And so our framework that we're going to use is we'll predict these weights on all the nodes of the graph, and then we use them to construct online fractional assignments. Good. So what are these weights? So each advertiser I has some weight WI. Good. And now using these weights, I can immediately decide how an impression would be assigned in the matching problem. So let Xij be the fractional allocation of impression J to advertiser I. So this is going to be the following. So you just look at all of your neighbor's weights. Good. And the amount you allocate to a particular neighbor is going to be its weights over the sum of the weights of the advertisers in your neighborhood. So it's just a proportional allocation according to these weights. And this will ensure that you're assigned to a full unit if all of your advertisers have remaining capacity. So this is the allocation. And notice here that this allocation is static. It doesn't depend on the other impressions. And so because of this, if you give me a set of weights, I can immediately decide how to allocate all of the impressions, no matter which order they arrive in. Good. Now, what you might be thinking is, well, why are these weights any good? It's not obvious at all that there should exist weights such that using this allocation actually results in a good assignment. However, it actually is true. So indeed, there exist weights that give a near optimal solution. And so for the matching problem, this comes from a paper of Argwal et al. And so they proved that you can compute a set of weights. So you give me the entire input instance offline, and I can compute a set of weights for any instance that would give me a 1 minus epsilon approximation using this fractional assignment. So like this proportional assignment. In our work, we extend this to general directed acyclic graphs, so the flow allocation problem. So this is one of the major technical innovations of our work. So it's a very intricate algorithm and analysis to show that to compute these weights for an instance and show that they work. And I think it's kind of nice because it shows that near optimal flows exist in a single source or single sink multiple source problem that encode the near optimal flow. So it's not obvious to me at all that you should be able to have a near optimal proportional flow in a directed acyclic graph. And further, the number of weights that we predict for this graph is O of the number of nodes in the graph. And of course, our graph could have n squared edges. So it's kind of nice that somehow only O of n information can encode an optimal flow on, say, up to n squared edges. Good. All right, so what are our results for these weights? Well, what we show is the following. So first of all, the weights are learnable. So learning these weights has sample complexity, polynomial in 1 over epsilon, and the number of advertisers offline nodes, such that we would get a 1 minus epsilon approximation. Now, here I'm hiding some assumptions about the instance, so I need to assume that the capacities of the advertisers are sufficiently large and that impressions drive independently in the distribution. And assuming this, though, we can prove that using a small number of instances, we can get back a collection of weights that would give me a 1 minus epsilon approximation and expectation. And here I'm comparing against the true optimal solution. So we have the learnability results for these weights. We supplement this in the work by another model for learnability. And then so I just want to briefly mention it here. So imagine that your impressions arrived in random order and you took an epsilon fraction of these impressions and just computed weights on those epsilon fraction. Well, then in fact, you can do that for the matching problem and it will result in a 1 minus epsilon approximation. So if you had the random order model, then this would give you a 1 minus epsilon approximation by just reading in an epsilon fraction of the impressions, compute the weights, and then just use them online for the rest of the impressions. And it doesn't even matter if they arrive in worst case order. So that grounds these weights in formal learnability. So then we want to prove that these weights are robust. So we show that that the weights, if they work well for one instance, then say they give you a 1 minus epsilon approximation for some instance, then for nearby instances, the quality degrades linearly in terms of the L1 norm difference between these two instances. So I'm not going to give, it's a bit technical, so I'm not going to give the exact expression here, but there is a slow degradation in terms of how much our input instances change between two instances. And then finally, the algorithm you can ensure gives you at least a maximal matching. So it guarantees that in the worst case, say for matching, you get a half approximation. For DAGs, you just look at the natural generalization of maximal matching, and it gives you that guarantee in the worst case. So this shows that these weights exist for matchings and flows. We show similar results for a related scheduling problem, and I just want to briefly mention this. So what is the scheduling problem? So imagine you're looking at the restricted assignment problem for minimizing makespan. So you have a collection of machines, jobs arrive online. When a job arrives, you assign it to a machine. And now, and that's irrevocable. And each job can only go to a subset of the machines. So a couple of years ago, there was a paper in SODA that showed that using similar weights, you can construct good allocations online, and they proved that this algorithm is parameter robust. And so here we extend that work to show that also the weights that they're using in that paper for allocating jobs to machines, those weights are indeed learnable by in this unknown distribution model by sampling a small number of instances proportional to 1 over epsilon and the number of machines. And further, the results can be extended to show they're instance robust, etc. And so it grounds that work where it was very unclear previously if these kind of magical weights that they were using for scheduling could actually be learned, and it grounds it in some formal model of learnability. Good. All right, so now what I want to do with just the remaining, I guess I'm almost running out of time, but maybe just a minute, is just some experimental results. So the goal of all of this is to eventually discover algorithms that are going to perform well in practice. So what I want to do is focus on the matching problem. And here we're going to look at a data set from Yahoo, search advertising data set over 123 days. And our baseline is going to be the water filling algorithm. This is the best deterministic algorithm for fractional assignments. And then we'll also look at the ranking algorithm, which was mentioned in one of the earlier talks, which is the best worst case integral algorithm. So both of these give you a 1 minus 1 over E approximation. And if you don't know what the ranking algorithm is, you just rank all of the, or take a random permutation of all of the advertisers. When an impression arrives, it finds the advertiser that it has the lowest rank in this list, and it matches itself there. And if there's no such advertiser, it doesn't match. So what is this water filling algorithm? So what water filling does is when an impression arrives, it just smears its allocation proportionally among the neighbors that have capacity. So in particular, it finds the neighbor that has the least proportion of remaining capacity and allocates it there. And if there's more than one of such advertiser, then it allocates itself evenly amongst them. So for instance, if this guy that's blue here arrives, well, then he can only go to B, so he fills them up. If this guy red arrives, he first goes to A and then spheres himself between the two. All right, good. So then we have our two algorithms, the proportional weights algorithm described, And we look at an improved version of this algorithm that this algorithm, instead of allocating proportionally, which could be to advertisers whose capacity is saturated, it instead only allocates proportionally to the advertisers that have remaining capacity. So what do we see? So the results are the following. So imagine the impressions arrive in random order. Well, then after about 20, if we use about 20% of our impressions to learn our weights, well, then our proportional weights algorithm is going to beat both of these baselines, which are here in black and yellow. And then it improves as we allow larger amounts of training. The improved proportional weights algorithm is really interesting. It starts out very high and very quickly moves up and then plateaus. So one takeaway from this, I think, is that these weights are indeed quite learnable. And there's more learnability experiments in the paper besides this. Finally, I just mentioned the robustness. So here, say you train on the previous day's impressions and use it on the next days. So we have the data that's indexed by days. What we observe is that when we do this, we actually get quite good performance for the improved version of our algorithm. So that's up here. Whereas if we compare to our baselines, they're about 5 or 6% worse. Unfortunately, the regular old proportional weights algorithm doesn't perform very well when it trains on the previous day. And I think the reason for this is that the impressions day to day, they just change by a lot. So something like the L1 norm difference between two input instances is something like 50% day to day. So we have this massive change in the impressions. And so I think it's pretty interesting that this improved proportional weights algorithm does so well. So that's what I wanted to say today. So as far as future work goes, I think some interesting questions for our community to answer is what are good models for incorporating these predictions into algorithm design? So what are the right models for learnability? What are the right models for robustness? And here I can imagine that there's many different possible models we can use. And I would really like to understand, the trade-offs between these models and how we can think about the performance guarantees of our algorithms and compare them across models. All right, thank you very much.
Thank you, Ben. We have time for one quick question, if there is one. The talk was very clear, but I don't see any questions in the chat. We have time for a quick question. Let me ask one question. So is there a way to view, I'm trying to wrap my head around your model. Is there a way to view the types of problems that you're thinking about as having as input effectively distributions over types of impressions? So you have like and interpret the robustness as kind of like a distribution shift, like robustness to distribution shift. So like if one day I have a particular mixture of impressions and the next day I get a similar but a little bit different, I don't want my learned weights to fail to give me what I was expecting.
Right.
Are like the instances like the types of
that's what I'm curious about, right? So if we're going to ground our predictions in these kinds of learnability, is this related to results that people have done in learning theory about distribution shift and these types of things? I don't know the connection, especially for some of these parameter robustness results. I'm not sure what the connection is, but I think it's a really interesting question to explore. So I just don't know the answer, I think, to your question.
All right, thank you. Thanks very much, Ben.